Hi class, welcome to the next section, chapter 2.2, properties of limits. Now that we have a decent idea of what a limit is, we can start to use the properties of limits to make calculating these things a little bit easier. Okay, so at this point we have about, I think, 10 properties that we'll go over. We'll talk about how to put them together to solve some of the easier limits without having to graph them or looking at them numerically by plugging in a bunch of values, right? So let's say that C is a real number, okay? It's an element of R, the real numbers, and that the limit of a function as x goes to a and that the limit of g of x as x goes to a both exist, okay? Then if I'm trying to take the limit of the two functions being added together or subtracted as x goes to a, I can separate those two functions to their separate functions and take the limit of each one separately, okay? So this is very useful for things like polynomials, right? X squared plus 3x. That's one function, but really if you think about it, it's two functions being added together. It's the x squared function being added with the 3x function. So what I can do is I consider it as two functions and break it down and just look at the two separately, and I could take their independent limits as they go to that value, whatever value I'm interested in, and then add those two limit values together, okay? So here what I'm doing is I'm looking at the function as a whole. Here I'm breaking it into pieces and I'm evaluating two separate limits. If I have a constant value, right, C is a real value, times a function, then I can pull that out as a scalar multiple and just take the limit of my function and then multiply it by that scalar amount. Okay, so for instance, 3x. I can just take the limit of the x function, and then whatever value I get out as the equation x goes to whatever number, and then just multiply it by whatever that constant was, in this case 3. Okay. If I have a function times a function as the function I'm taking the limit of, I can separate that into two separate functions as well and take their product. If I have a division of functions, right, so for instance, a rational function, I can just take the limit of the two functions separately. Take the limit of the top, take the limit of the bottom, and divide those two numbers, as long as my denominator does not go to 0. Okay, so my pre-calc class students will recognize this. ST means such that, right? So the limit of this rational function is equal to the limit of the top divided by the limit of the bottom, such that the bottom value is not 0. Okay. If my function is being raised to a power, so it could be like x cubed, that's the function x to the cubed power, to the third power, right? It's the same thing as if I just find the limit of that x function or whatever function it is to whatever power. So I take the limit of my function and then I just raise that number to the power. So remember, whenever we have limit of the function, this is a number. So here I'm taking the limit of a function. That function happens to be, maybe it's sine squared, for instance, right? It would be the same thing as if I found the limit of sine as I approach this value and then just squared my output that I got for that limit. Okay. The limit of a constant value is just that constant value, right? So if my function is like 5, it's always 5. It's very plain to see that as I approach from the left or from the right for any value, I'm just going to approach the output value of 5 because my function is always 5, right? So the limit of a constant value is that constant value. The limit of a line, okay, the standard line y equals x, the limit as x goes to whatever value of interest you're looking at is just going to be that value, right? So if I'm looking at the limit of x as x goes to 7, that's going to equal 7, right? The limit of x to the nth power, as x goes to a, is a to the nth power. So it's very similar to me using rule 7 and rule 5 together, right? Since my function is just a line being raised to whatever power, well, I would basically be having a to the nth power, right? So rule 8 is rule 7 and rule 5 being put together. Okay. And this is as long as n is a positive integer. Okay, positive integer. If x is the nth root, then the limit as x goes to a is just the nth root of a, again, n being a positive integer. And here, if my function, right, is the nth root of my function, then I can just take the limit of my function as x goes to a, and then take the nth root of that. So rule 10 is really just rule 5. Okay, it's just that that power that I'm using is a fractional power, because we know that fractional powers are nth roots. And is an integer. Okay, so let's go ahead and do an example. So we're going to look at this limit for the function 2x squared minus 3x plus 1. And we're going to look at what happens as x goes to 1. Now, instead of graphing this and looking at the graph and saying, oh, okay, as I look at 1, this is what's happening from the left and what's from the right, instead of plugging in a bunch of values as I get close to 1, like we did before as well. So, for instance, plugging in 0.8, 0.9, 0.99, 0.999, 0.999 to come from the left. Come from the right, plugging in 1.1, 1.01, 1.0001, 1.00001, right? So instead of squeezing in from the left and the right and looking at what my function does, we're going to break this down using the properties of limits, okay? So the first property we're going to use is we're going to recognize that this function, this polynomial function I have, is a bunch of functions being added together, okay? So I get to use this property 1. Instead of looking at it as one whole thing, I'm going to break it down into its independent pieces where each term that I have, separated by plus or minus, is a different function, okay? So that's what I'm going to do first. So I take my function here, and I'm going to take the limit of the first function. I'm going to subtract from that the limit of the next function, 3x, plus the limit of the last function, which is a constant function, right? So now, instead of taking the limit of the whole thing, I'm taking the limit of the individual terms, because each individual term is a function. Now, for 2x squared, I can break this down more by using several rules, okay? One of those rules being rule 2. A constant times a function means I can take the limit of my function and then in the end multiply it by a constant. I also have the rule that I am taking a function to the nth power, in this case x squared. So we saw that here, right? So I can break down the first term using rule 2 and rule 8. The limit of 1 as x goes to the negative 1 is just 1, right? So for the last term, okay, I'm taking the limit of a constant value as I go to a value. This is rule 2. I have a constant value, I have the function x, and I'm multiplying it by a constant 3. So that is rule 7 mixed with rule 2, right? Constant times a function, and the limit as x goes to 1 of x is just going to be 1 in that case, right? Okay. So I can pull out my constants, okay? So that's using rule 2, the constant rule. And then this is the next rule that I would simplify, because this is the limit of x squared, right? So squaring the limit, instead of taking the limit of x squared, it's the squared value of the limit of x. Okay. And so now I have everything that I need to. I know that the rule for the limit of x as x goes to some value is just that value, right? That's rule 7. Rule 7. Okay. The limit of x as x goes to the value is just that value. Okay, so I'm here. So then this is going to be 2 times 1 squared. Okay, this is going to be 3 times 1, because the limit of x as x goes to 1 is 1. And a limit of a constant value is always that constant value. So I went from a limit of a single function to breaking down this limit as far as possible, so that it's a bunch of the limit of just x as x goes somewhere. And then from here, I know what these values are, and I just plug everything in. Okay. And I know that I get out 0, because I have 2 minus 3 plus 1 more, so that's 3 minus 3 is 0. So that's how we break down limits, right? So this brings us to a theorem, which is that if I have a function f and a function g, and g is always larger than or equal to f when I'm close to some point of interest, a, okay, except possibly at that point, so it's possible that at the value I'm looking at, f is actually larger than g, okay, it's possible. And the limits of f and g both exist as I approach that value, then the limit for f is always going to be less than or equal to my limit for g. So basically, if g is always bigger than f, then the limit of f is always less than the limit of g, okay? But equality holds there as well. Okay, so our next theorem that has to do with, that's derived basically right from this is called the Squeeze Theorem, right? So here we're saying that f is always less than or equal to h, and h is always less than or equal to g, right? So h is always in between f and g, or possibly equal to them. There could be points where all three of them are equal. Okay. Then the limit of f as I approach a value a is going to be equal to the limit of g as x approaches a. So h is always between f and g, but the limit of f and the limit of g are equal at some point a, then the limit of h has to be equal to that limit as well. So that's called the Squeeze Theorem or the Sandwich Theorem. It's basically saying that I always have a function that's between two other functions. And so if my two functions that bound that middle function, right? Because this is always in between these two. So it's never less than this and it's never larger than this. So it's bounded by two other functions. If those two functions have the same limit at a point, well, that means that that middle function has been squeezed in between there as well, because it's always bounded by those other functions. So it has the same limit also. We like to use this theorem when it's very, very difficult to evaluate the limit of h. When I can't find the limit of this, but I know a function that's always smaller than it and a function that's always larger than it, and if they kind of go to the same limit at some point, then I can say, maybe I can't calculate h, but by the Squeeze Theorem, I can figure out what the limit is, right? So here's a graphical representation. So I have f, which is a lower bound function. I have g, which is a higher bound function. And I have some function h that's always in between those. So if there's a point where f and g have a limit that they agree on, h has to have a limit of that value also.